In 1989, United Airlines Flight 232 was just cruising along at 37,000 feet when the tail engine suddenly detonated.
Just completely blew apart.
Yeah, literally blew apart, and it severed all three hydraulic lines, which completely crippled the aircraft.
Right, they had absolutely no flight controls.
None. But the pilots miraculously managed to crash land the plane in Sioux City, Iowa, and they saved over 100 lives in what is, honestly, still considered a masterclass in aviation survival.
Oh, absolutely. It's studied to this day.
Right. But when the investigators finally dug into the wreckage to find the root cause of the explosion, they didn't find, a massive terrorist bomb.
No.
And they didn't find some huge systemic computer failure either. What they found was a microscopic, almost invisible crack inside a single spinning titanium fan disc inside the engine.
A tiny, tiny flaw.
Exactly. A tiny flaw that had been created during the forging process years earlier.
Right.
And it had just been subjected to the relentless, invisible violence of continuous rotation until the metal simply gave up.
It is a really sobering reminder of the absolute razor's edge that modern civilization operates on.
Yeah.
I mean, we walk into factories, we board airplanes, we open our refrigerators, and we are just constantly surrounded by this quiet, predictable hum of machines.
We don't even think about it.
We don't. But that hum is a carefully constructed illusion. Beneath the casing of every motor and turbine out there, there is an environment of intense kinetic energy, extreme centrifugal forces, and just brutal mechanical stress.
Which brings us to what we are looking at today. We've got a fascinating stack of notes on the hidden architecture that actually tames all that chaos. We are doing a deep dive into rotating core components.
The parts that spin, generate rotation, or receive rotational force.
Right. The bridge between the raw, messy energy of nature like, wind, expanding gas, rushing water, and the hyper-organized world we actually live in.
It's what makes modern life possible.
It really is. And the notes we have today introduce a surprisingly philosophical, almost poetic framework for looking at these physical parts. They reference a 2025 reflection piece called Leading Under Starlight.
Yeah, I love this part of the material.
It's so good. It outlines a leadership persona, like a subpersonality, named Bannock. And Bannock isn't the loud, spotlight-seeking CEO type.
Not at all.
Bannock is a quiet compass. It's a leadership style entirely focused on holding the center, carrying the heavy load in the dark, and allowing the rest of the system to move and thrive without ever demanding applause.
Which is such a brilliant way to frame the physical world.
Exactly. These 8 mechanical components we are going to explore today, rotors, stators, shafts, spindles, axles, flywheels, armatures, and hubs, they are the Bannock of our physical infrastructure.
They hold the center.
They really are the turning heart of civilization.
And the scale of what that turning heart is responsible for, it's difficult to overstate. Just to establish the sheer stakes of what we're looking at, the source notes pull data from the International Energy Agency, the IEA.
Right. And their recent figures state that electric motor systems alone account for 53% of global electricity consumption.
Wait, really? More than half?
More than half of all the electrical power generated on Earth goes into making something spin around a central axis.
That is insane. So we aren't talking about a niche subset of engineering here.
Well, not at all. If you remove these rotating components, society wouldn't just slow down, it would instantly devolve back to the 17th century.
Wow.
They are the invisible load bearers for everything from data center cooling systems to global power grids.
Okay, let's unpack this, because before we get into the specific crew members of this mechanical ship, I think we have to look at the physics.
Yeah, we have to understand the environment.
Right, we need to shift from the philosophical idea of holding the center to the raw physics of what is actually being held. Why is rotation the ultimate answer for doing work? Because, if you look at early industrialization or even just the internal combustion engine in a modern car, we use a lot of linear motion.
Sure, pistons, hydraulic rams. Yeah, a piston pushing straight down, a hydraulic ram extending. If linear motion is so powerful, why do we constantly convert it into rotation the second we get the chance?
Well, because linear motion contains a fundamental mechanical contradiction. To do continuous work, it must constantly defeat its own momentum.
Okay, what do you mean by that?
So, if you ignite fuel in a cylinder, the expanding gas drives the piston in a straight line, right? And it is incredibly powerful.
Right.
But eventually, the piston reaches the end of the cylinder.
Right, or runs out of room.
Exactly. So to harness that power again, the piston has to decelerate to an absolute stop completely reverses direction, travel all the way back up, stop again, and wait for the next explosion.
So you are spending a massive amount of energy just to fight the mass of the piston itself. You're constantly accelerating and decelerating heavy metal.
Precisely.
Yeah.
That stopping and starting is incredibly jarring. It creates massive vibration, it wastes enormous amounts of energy through inertial losses, and it's mechanically violent to the surrounding structures.
So rotation solves this.
Rotation solves the problem of continuous work because it never has to reverse direction. A spinning shaft gives energy a repeatable, infinite pattern around a fixed axis.
Right.
It delivers power second after second, hour after hour, with a smooth, continuous flow.
But that flow, that smooth hum we hear, it's actually deceiving, isn't it?
Slightly deceiving.
Because the forces at play on these rotating parts are staggering. The primary language of rotation is torque. Now, we often think of torque just as the twisting force you use when you turn a wrench.
Right, like tightening a bolt.
Yeah.
Yeah.
But for a piece of machinery like a massive drive shaft, it's a constant state of internal war. I like to think of it like taking a soaking wet towel and twisting it with both hands to wring out the water.
Oh, that's a great analogy.
The fabric is fighting you, one end is being twisted, the other end is resisting, and all those internal fibers are screaming. That is essentially what is happening inside a solid steel shaft.
Yeah, it's a fantastic way to conceptualize torsional shear stress. The motor is twisting one end of the shaft, the heavy machinery on the other end is resisting, and the molecular lattice of the steel is fighting to keep its shape.
The shaft is literally twisting.
It is twisting, even if that twist is microscopic and completely invisible to the naked eye. But torque is really just the beginning of the abuse.
Oh, great. There's more.
Oh, yeah. As you apply torque, you introduce bending moments. You introduce tension on one side of the component and compression on the other. And what is vital to understand here, and what brings us right back to the tragic example of Flight 232, is that rotating parts very rarely fail because of one massive, overwhelming load.
Right, they don't usually break because a machine just suddenly pulled too hard.
Exactly. They fail from a phenomenon called high cycle fatigue.
Okay, I really want to dig into fatigue because honestly, it feels kind of counterintuitive.
How so?
Well, if I have a heavy steel rod, and I know for a fact it can support 1,000 pounds, and I only put 100 pounds on it, it should last forever, right? But rotation changes the math completely.
It absolutely changes the math because rotation introduces alternating stress.
Alternating stress.
Yeah. Imagine a solid steel shaft acting as a bridge between an electric motor and a heavy industrial fan. The sheer weight of those massive fan blades pulls downward, causing the shaft to sag downward in the middle.
Even a thick steel shaft sags.
Yes, even solid steel sags. We are talking about a deflection of maybe a few thousandths of an inch, but it is real. Because of that downward sag, the metal molecules on the top surface of the shaft are being squished together in compression, and the metal molecules on the bottom surface are being stretched apart in tension.
But right, like bending a stick over your knee. The top squishes, the bottom stretches.
Exactly. And then you turn the motor on.
And the nightmare begins.
The moment the shaft begins to rotate, the spot on the surface that was at the top, being squished in compression, rotates 180 degrees to the bottom.
Where it's instantly stretched in tension.
Right. And then another 180 degrees, it's squished again. Stretch, squish, stretch, squish. If that shaft is spinning at a standard 3,600 revolutions per minute, every single molecule on the outer surface of that steel is going through a complete reversal of stress 60 times a second.
60 times a second. That is wild. And this is where the Volar curve, the SN curve, comes into play in the source notes, right?
Yes, the SN curve maps this out perfectly. S stands for stress, N stands for the number of cycles. Engineers use this curve to predict exactly how many of these alternating stress cycles a specific material can take before a microscopic crack forms.
Because it's not really about the metal getting tired in like a biological sense.
No, not at all.
It's about a tiny defect, maybe a tiny scratch left by a lathe during manufacturing, or a microscopic inclusion in the steel alloy acting as a stress concentrator.
Exactly. The stress concentrates at that tiny flaw, and maybe the shaft handles it fine for a month or a year. But after 10 million cycles, the molecular bonds at the tip of that microscopic scratch finally yield.
And a tiny crack opens up.
Yeah. Then, with every single subsequent rotation, as the crack is pulled open and squished shut, the crack advances a fraction of a micron.
Just creeping through the metal.
Creeping. And this actually leaves distinct markers inside the metal called beach marks or striations, which is exactly what investigators look for after a crash.
Oh, wow. So they can literally see the history of the crack growing.
Yes. The crack grows deeper and deeper into the shaft, which reduces the amount of healthy metal left to carry the load. Until one Tuesday afternoon, the remaining healthy metal is finally overwhelmed by the torque, and the entire shaft snaps violently.
Just brutal. And as if twisting and fatigue weren't terrifying enough, you also have the physics of rotor dynamics and critical speeds.
Yes, resonance.
This part blew my mind. The idea that a machine can destroy itself simply by spinning at the wrong speed without any external force acting on it at all.
It's a phenomenon entirely related to natural frequency. Every physical object in the universe has a natural frequency, a specific acoustic rhythm that it naturally vibrates at if you strike it.
Like ringing a bell.
Like ringing a bell, exactly. And a spinning rotor or shaft is no different. As it spins up, it generates vibration. If the rotational speed and RPM happens to align perfectly with the natural frequency of that mechanical assembly, the system hits a state of resonance.
When I read this, I immediately pictured that famous old black and white footage of the Tacoma Narrows Bridge tearing itself apart in the wind.
Oh, perfect example.
The wind just happened to match the bridge's natural frequency, and the vibrations just compounded until concrete and steel were waving like a ribbon.
That is exactly the same physics just applied to a spinning shaft. Engineers map this out using what are called Campbell diagrams.
Campbell diagrams, right?
Yeah, they use them to track how the natural frequencies shift as the machine speeds up. Because if a turbine operator lets a machine dwell at its critical speed for too long, the microscopic vibrations synchronize and they amplify exponentially.
So the wobble just feeds on itself.
It does. And within seconds, a massive steel rotor can begin whipping outward with such violent force that it obliterates the bearings, shatters the casing, and sends shrapnel flying across a factory floor.
Here's where it gets really interesting. Now that we have established this absolute war zone of physics, the relentless torsional shear, the high cycle fatigue, the threat of catastrophic resonance, let's meet the specific crew members.
The Bannock of the machine.
Exactly. We're moving from the abstract physics of the environment to the physical roster of parts designed to actually survive it. The sources categorize our 8 components based on their role in the system. Let's start with the energy converters, the rotor, the stator, and the armature.
Okay, so the rotor and the stator form the foundational pairing of the electrical age. You will find them at the heart of almost every single electric motor and generator on the planet.
They are the dynamic duo.
They really are. They define the transition point where electrical energy becomes mechanical motion, or vice versa if it's a generator. The stator is, true to its name, the stationary element.
Right, static.
Stator. Yeah. It's typically an outer cylindrical housing built from stacked laminations of steel, and it's lined with intricate coils of copper wire. Now, when alternating current flows through those coils, it doesn't create a static magnetic field. It creates a rotating magnetic field that sweeps around the inside of the stator.
Okay, I was really trying to visualize exactly how this interaction works when I read the notes, rather than just accepting it as, magic.
It's basically magic, but we can explain it.
Well, because if the stator doesn't physically move, how does it force the rotor to spin? The rotating magnetic field you just mentioned, I picture it like a phantom force running laps around the inside of the motor housing.
That's a great visual.
And the rotor, which is the physical cylinder sitting inside that empty space, just gets caught in the current.
Exactly. Let's look at the most common industrial workhorse out there, the AC induction motor. The stator's rotating magnetic field sweeps across the metal bars of the rotor. And according to Faraday's law of induction, that moving magnetic field induces an electrical current directly into the rotor itself.
Even though there are no wires physically connecting them.
None at all. It's purely induced across the air gap. That induced current turns the rotor into its own electromagnet.
So now you have 2 magnetic fields.
Right. And through what we call the Lorentz force, the rotor's new magnetic field interacts with the stator's rotating magnetic field. The rotor is essentially compelled to chase the stator's field around in circles.
Like it's trying to catch up to the phantom force running laps.
Yes, but here is the brilliant mechanical catch. The rotor can never quite catch up to the speed of the magnetic field.
Wait, why not?
Because if it did catch up, the relative motion between the 2 fields would drop to 0. And if relative motion drops to 0, no current gets induced, and the torque vanishes.
Oh, wow. So it has to constantly fall just a tiny bit behind to keep working.
Exactly. That tiny difference in speed is called slip. And slip is the mechanism that allows the motor to maintain continuous torque under heavy loads.
It is an incredible piece of physics. I kind of view it like the stator is the walls of a dance floor, right? It provides the discipline and the boundaries. It orchestrates the magnetic field.
I like that.
And the rotor is the dancer. It's the physical manifestation of that invisible dance, turning it into raw, usable torque.
It turns the electric phantom into physical force.
Yeah. And what about the third energy converter in our stack, the armature?
The armature is the active power carrying component, but the term is most frequently applied to direct current, or DC systems.
Okay, so unlike the AC induction motor.
Right. In a classic DC motor, like the starter motor in your car, or the motor in a heavy-duty power drill, the armature is the part that actually rotates. It is wrapped in coils of wire, and electrical current is fed directly into it through these carbon brushes that push against a commutator.
So it's making physical contact.
It is. The magnetic field of the armature constantly flips its polarity as it spins, pushing and pulling against permanent magnets stationed in the surrounding housing, and that creates continuous rotation.
Okay, so the converters do the heavy lifting of changing the state of the energy. But torque, trapped inside a motor housing, is basically useless.
Totally useless.
It has to go somewhere to do work, which brings us to our power transmitters. The shaft, the axle, and the hub. We've talked a bit about the shaft already, enduring all that twisting and fatigue. But I love how the notes poetically call the shaft a promise.
A physical promise.
Yeah, the promise that the motion generated here will reliably arrive over there.
It really is the messenger of the system. Whether it is a tiny millimeter-thick shaft inside a medical drill or a massive multi-ton drive shaft connecting a container ship's engine to its propeller, its job is absolute fidelity in transmitting torque.
But wait, how do you differentiate a shaft from an axle? Because honestly, if I look under a truck, I see a heavy metal bar connecting the two wheels. Some people call it an axle, some people call it a drive shaft.
Yeah, the terms get tangled up a lot.
What is the fundamental engineering distinction between the two?
It really comes down to their primary loading condition and their purpose. A shaft's primary purpose is to transmit torque.
Okay.
It is designed specifically to endure torsional shear stress, that wet towel twisting we talked about. An axle, on the other hand, is primarily designed to support a load.
So it's about weight, not twist.
Exactly. Think of a traditional horse-drawn wagon. The heavy iron rod connecting the two wooden wheels doesn't spin. The wagon just rests on it, putting it under extreme bending stress, and the wheels just rotate around the ends of it on bearings. That is a pure axle.
So an axle carries the weight of the world, while a shaft carries the power.
That's a very poetic way to put it, yeah. Now, in modern automotive engineering, things do get blended. The drive axle on your car has to support the weight of the vehicle while simultaneously transmitting the torque from the transmission to the wheels.
Oh, so it's doing double duty.
Exactly, enduring both heavy bending moments and intense torsional shear simultaneously, which is why automotive axle design is incredibly complex.
And completing this trio of transmitters is the hub. The hub is the critical gathering point. It's the mediator.
The mediator, yes.
Because, you can't just weld a rubber tire directly to a steel axle,
Yeah.
and you can't weld giant composite wind turbine blades directly to a generator shaft. You need a transition zone.
Right, you need a way to spread the force out.
So the hub is that heavy, often complex metallic center that locks onto the shaft, usually via splines, right? Which are like interlocking metallic teeth.
Or heavy QAs, yeah.
And then it provides a massive flanged surface to bolt on the outer structures.
The hub is where the localized, highly concentrated torque of a small diameter shaft is distributed outward into the much larger diameter of the working component, whether that's a wheel, a fan, or a huge turbine blade.
It spreads the load.
It does. But the mechanical interface between the hub and the shaft is a notorious point of failure.
Oh, really?
Oh, yeah. If there's even a microscopic amount of play in those interlocking splines, the continuous reversing forces will just hammer that tiny gap. Over time, it'll hammer it until the splines shear completely off, leaving the shaft just spinning uselessly inside a broken hub.
Ouch. Which naturally leads us to the final category of our crew, the specialists of precision and memory, the spindle and the flywheel.
Two very different but crucial components.
So the spindle is the ultimate precision specialist. I'm thinking of the central spinning axis inside a multi-axis CNC milling machine or like a high-end hard drive.
Yes, spindles operate in an entirely different paradigm than standard drive shafts. A standard drive shaft just needs to be tough and not break under torque. A spindle is absolutely obsessed with microscopic accuracy.
It's the perfectionist of the Bannock crew.
It really is. It doesn't just hold a cutting tool and spin it. It has to hold it in the state of near-perfect rigidity while subjected to brutal, erratic cutting forces.
The key metric the notes highlight here is runout. Can you explain runout? Because this seems to be the god that all machinists pray to.
Runout is everything. It's the measure of how much a spinning object wobbles off its true, perfect center axis.
Okay, so wobble.
Right. So if you have a CNC machine cutting a critical aerospace component out of a block of titanium, and the spindle holding the cutting tool has a runout of even a few microns.
Which is what, fractions of the width of a human hair?
Exactly. Almost nothing. But that tiny wobble is transferred directly into the metal being cut. A hole that was supposed to be perfectly round becomes slightly oval. An edge that's supposed to be perfectly flat gets a microscopic wave in it.
And suddenly the part doesn't fit the airplane.
Bingo. In high-precision manufacturing, excessive spindle runout turns extremely expensive raw materials into scrap metal.
Wow.
And achieving zero runout requires incredibly precise angular contact bearings and even thermal management. Because even the heat generated by the spinning bearings can cause the spindle shaft to expand unevenly and ruin the tolerance.
That is wild. You have to cool the spindle just so the metal doesn't warp a few microns.
Yes, the thermodynamics are critical.
And if the spindle is the precision specialist, the flywheel is the steady elder of the machine.
The elder, yeah.
I just love the concept of the flywheel. Its entire job is to store rotational kinetic energy and smooth out the erratic nature of the real world.
Exactly. We discussed earlier how a piston engine provides power in violent, sudden pulses.
Right, bang, stop, bang, stop.
Yeah. Every time a cylinder fires, it delivers a massive spike of torque to the crankshaft, followed by a momentary gap in power before the next cylinder fires. If you connected that erratic pulsing rotation directly to a transmission, it would shatter the gears.
So you bolt a massive, heavy disc of metal, the flywheel, to the end of the crankshaft.
And when that sudden spike of torque hits, the sheer mass of the flywheel resists the sudden acceleration. It absorbs the energy by speeding up just a tiny, tiny bit.
And then during the dead space between pulses,
During the dead space, the momentum of the heavy spinning metal keeps the shaft turning, effectively giving the energy back to the system.
it is literal mechanical patience. It just carries the momentum through the rough patches.
It is patience,
Yeah.
yeah. But what is truly fascinating here is the underlying physics of how a flywheel stores that kinetic energy and how engineers manipulate that math.
Oh, the formula in the notes.
Yes, the source text provides the classical formula for rotational kinetic energy. E equals 1/2 I omega squared.
Okay, let's break that down for everyone listening, because the implications of that equation actually dictate how modern machinery is built.
Let's do it.
So E is the total stored energy. E is the moment of inertia, which is basically a combination of how heavy the flywheel is and how far away that mass is from the center.
Right, the geometry of the mass.
And the omega symbol, the Greek letter, represents the angular velocity or simply the speed of rotation.
The crucial detail in that formula is that the omega is squared. The relationship is not linear.
Right.
If an engineer wants to double the amount of energy a flywheel can store, they could, double the physical weight of the flywheel. But adding massive amounts of weight makes machines sluggish, heavy, and really hard to transport.
But if they instead make the flywheel spin twice as fast, because that speed is squared in the equation, the flywheel now stores 4 times the energy.
Exactly.
If they make it spin 3 times as fast, it stores 9 times the energy. Making it spin faster is literally a massive cheat code for energy storage.
It is a cheat code, but it is an incredibly dangerous one.
Because of the forces.
Because while the stored kinetic energy increases by the square of the speed, the centrifugal forces, the literal stress trying to rip the atoms of the metal apart, also increases exponentially.
Right.
As the flywheel spins faster and faster, a phenomenon called hoop stress builds up inside the metal. The outer edges of the disc are pulling away from the center with terrifying force. If a heavy standard cast iron flywheel is spun up to these hyper-efficient speeds, it reaches what we call its burst speed.
Burst speed.
Yeah, the metal simply cannot hold itself together, and the flywheel detonates like a fragmentation grenade.
Which perfectly sets up our next major question. Knowing that these components must survive extreme hoop stress, endless high cycle fatigue, and brutal torque, how do we actually construct them?
What are they made of?
Yeah, what are they made of? We have to shift our focus from the shape of the parts down to the molecular lattice. Let's explore the heavy hitters of material science: steel, cast iron, and aluminum.
Well, steel is, without question, the undisputed king of the rotating world.
The king.
It is the default material for any serious mechanical application. The reason steel dominates the manufacturing of shafts, axles, and high-stress rotors is its unique ability to be manipulated.
Manipulated how?
By altering the carbon content and the thermal history of the steel, engineers can perfectly balance three critical properties: tensile strength to resist being pulled apart, toughness to absorb sudden impacts without shattering, and machinability so it can actually be cut to the precise micron-level tolerances we discussed with spindles.
But the notes draw a very sharp line regarding how that steel or iron is formed, the difference between casting and forging.
It's a huge difference.
And I'll admit, before diving into these sources, I kind of assumed metal was metal. But the manufacturing process completely alters the molecular reality of the part.
It changes everything.
So casting is essentially pouring liquid metal into a mold. I pictured it like pouring cake batter into a pan. You melt the iron, you pour it in, and as it cools, it takes the shape perfectly.
Yes, casting is highly efficient for creating large, complex geometries. And cast iron, specifically gray cast iron, has a unique advantage that makes it highly desirable for certain applications.
Which is?
Well, as the liquid cast iron cools, the carbon inside it precipitates out into tiny, microscopic flakes of graphite suspended throughout the iron matrix.
Wait, if forging aligns the grain and makes things tougher, which we'll get to, why do we cast engine blocks or heavy machine bases at all? Is it purely just companies being cheap, or is there a mechanical advantage to that random, flaky grain structure?
It is not just cost at all. It is a profound mechanical advantage. Those graphite flakes act as internal shock absorbers.
Oh, really?
Yes. They give gray cast iron an incredible ability to damp vibrations. If you build a massive CNC lathe, you don't want the frame transmitting vibrations from the factory floor directly into your precision spindle. You build the heavy base out of cast iron so it absorbs and neutralizes the acoustic energy.
That makes total sense.
But those same graphite flakes are also stress concentrators. They make cast iron relatively brittle under tension.
So you wouldn't use it for a shaft?
Exactly. If you try to use cast iron for a high-speed, high-torque drive shaft, those flakes become the starting points for the microscopic fatigue cracks we discussed earlier.
Which is why we forge the high-stress part.
Yes.
Forging is the complete opposite of pouring cake batter. Forging is like kneading really dense dough under immense pressure.
Perfect analogy.
You take a solid, glowing hot block of steel, and you smash it, press it, and hammer it into the shape of a shaft or an axle using thousands of tons of hydraulic pressure.
And the metallurgical transformation during forging is profound. As the metal is deformed under pressure, the internal grain boundaries, the crystalline structures of the steel, are elongated and forced to align with the physical contours of the part.
They flow with the shape.
Yes, it creates continuous flowing grain lines that follow the shape of the shaft, completely eliminating the internal voids and random structures found in castings.
Wow.
A forged steel shaft possesses exceptional resistance to fatigue and shear stress because the molecular lattice has literally been woven into a continuous, cohesive structure.
It's the difference between cutting a shape out of particle board versus cutting it out of solid, straight-grained oak.
The grain alignment gives it strength.
But beyond these massive structural metals, the turning heart relies on very specific specialty materials. I mean, you cannot build a stator or an armature out of steel alone.
No, you need materials that manipulate electromagnetism, not just mechanical stress. Copper is absolutely vital here.
Right.
Stators and armatures are packed with miles of tightly wound copper wire. Its low electrical resistance means it can carry massive amounts of current efficiently.
But even copper has its limits, right? The notes mention things like skin effect in high-frequency AC motors, where the electrical current gets pushed to the outer surface of the copper wire, meaning the center of the wire is basically wasted space.
Yeah, at high frequencies, the current travels on the skin.
And more importantly, the thermal limits. The efficiency of a motor is often bottlenecked not by the metal itself, but by the ultra-thin layer of varnish insulating the copper wire from short-circuiting against itself.
That varnish is a major fail point.
If you push too much torque, the copper heats up, the varnish melts, and the motor goes up in smoke.
Precisely. This is why motor stators are classified by insulation classes like Class F or Class H, which dictate the maximum operating temperature the resins can survive before catastrophic failure.
But when we look at the absolute cutting edge of rotation high-performance electric vehicle motors, hyper-efficient wind turbines, advanced robotics, The discussion immediately turns to rare earth elements.
Right, neodymium and dysprosium.
Yes. When neodymium, iron, and boron are alloyed together, the unique electron spin alignment in the orbitals of the neodymium atoms creates a permanent magnet of astonishing, almost terrifying power.
Terrifying.
Well, they're so strong they can crush your fingers if two of them snap together.
Oh, wow.
Before the mass commercialization of neodymium magnets, electric motors had to be relatively large and heavy to generate substantial torque. But by embedding rare earth permanent magnets directly into the spinning rotor, engineers can create motors that are incredibly compact, lightweight, and capable of delivering massive torque instantly.
It's the metallurgical breakthrough that made modern electric vehicles viable.
It absolutely is. You couldn't build a Tesla without them.
And the sources also touch on ceramics and composites. We are seeing carbon fiber drive shafts or carbon fiber sleeves wrapped around rotors to prevent them from bursting at high speeds.
Right, to contain that hoop stress we talked about.
Yeah.
And we're also seeing silicon nitride ceramic bearings.
Why ceramics?
Ceramics are deployed in high-stress environments for a few key reasons. First, they are incredibly hard and resistant to thermal expansion, meaning they hold their shape flawlessly at high RPMs.
No runout issues.
Exactly. Second, they are highly resistant to rolling contact fatigue. And crucially, for electric vehicle applications, ceramics are dielectric.
Dielectric, meaning they don't conduct electricity.
They do not conduct electricity. In high-voltage AC motors, stray electrical currents can actually arc across standard steel bearings, literally welding tiny pits into the metal surface. A destructive process known as electrical fluting.
Sparks inside the bearing.
Yes, ceramic bearings act as an insulator, breaking the electrical path and saving the bearing.
But they bring their own trade-offs, obviously. A ceramic bearing ball might be hard as a diamond, but it is brittle. It can't handle shock loads like a forged steel ball can.
Right.
But let's look at how all this metal is finalized, because getting the shape right is really only half the battle. The manufacturing process of a shaft or a gear usually concludes with heat treatment, which the name suggests is basically industrial alchemy.
It really is alchemy. Carburizing, quenching, tempering.
It's a phenomenal balancing act. The holy grail for an engineer designing a rotating component, say a spline drive shaft, is a part that is incredibly hard on the outside but tough and ductile on the inside.
Yes.
Because you need the outer surface of the shaft to be hard like glass so that the bearings spinning against it don't immediately wear a groove into the metal. But if you made the entire solid shaft out of glass-hard metal, it would be too brittle.
The moment a shockload of torque hit it, the entire shaft would snap in half.
So how do they get both?
Through selective heat treatment. In a process like case hardening or carburizing, the forged steel shaft is placed in a carbon-rich environment and heated until it glows.
Okay.
The surface of the steel absorbs extra carbon atoms into its lattice structure. Then the shaft is rapidly cooled or quenched in oil or water.
Just dropping it in cold liquid.
Right. This rapid cooling traps the carbon atoms and forces the surface lattice into a highly stressed, needle-like structure called martensite. The outer millimeter of the shaft becomes incredibly hard.
But the inside stays soft.
Yes, because the cooling process doesn't fully penetrate instantly to the core, the center of the shaft remains in a softer, more ductile state. You literally create a glass-hard armor shell wrapped around a flexible, shock-absorbing core.
That is just brilliant. But a perfectly forged, flawlessly case-hardened steel shaft is completely useless if it doesn't fit the machine perfectly.
Right, it has to fit.
Which transitions us from the art of making the part to the rigid, uncompromising language of identifying and measuring the part. Because the tolerances we are dealing with are invisible.
This is the domain of precision specifications, and the source notes highlight a massive vulnerability in maintenance cultures. The danger of looks right.
Looks right.
Yeah, you can have a technician holding two pump shafts in their hands. To the human eye, they are perfectly identical. Same length, same diameter, same color, same weight.
They look exactly the same.
But one is a certified original equipment manufacturer, or OEM, part, forged from specific alloy steel and heat-treated to exact specifications. The other is a cheap, generic aftermarket copy milled out of mild, untreated steel.
The human eye sees the shape. The machine feels the specification.
That's exactly right.
If you install that generic shaft into a high-pressure boiler feed pump spinning at 4,000 RPM, it might slide into the housing perfectly. But because the bearing seat was machined just 10 microns undersize, or because the mild steel lacks that tempered martensite shell we just talked about, it begins to wear immediately.
And that tiny bit of wear introduces vibration.
The vibration destroys the seals. And within a week, the shaft snaps, the pump destroys itself, and you have a catastrophic multi-million-dollar shutdown. All because someone assumed looks right is good enough.
The language of rotating components is absolute. The notes provide a highly specific example of this with a standard bearing code. 6205 2RSC3.
Okay, I want to talk about this. To a layperson, that looks like a random string of barcode numbers.
Just a part number.
Yeah. But to an engineer, it is a highly specific mechanical sentence. Let's translate that sentence. What does it actually tell us?
So the first part, 6205, dictates the exact dimensional series of the bearing. It's the inner bore diameter, the outer diameter, and the width. It ensures the part physically fits the hole.
Okay, simple enough.
Then 2RS specifies the sealing arrangement. It stands for two rubber seals, meaning the bearing is factory packed with grease and sealed on both sides to keep dust and moisture out of the rolling element.
Got it.
But the final designation, C3, is where catastrophic mistakes are made.
Explain the C3 clearance, because I love analogies that make this invisible stuff click. To me, it sounds like leaving expansion gaps in a bridge. In the summer heat, the concrete expands, and if there wasn't a gap, the bridge would buckle.
That is a perfect analogy. C3 designates the internal radial clearance of the bearing. It means that when the bearing is manufactured at room temperature, there is a microscopically larger gap between the steel balls and the metal raceways than in a standard bearing.
So it's intentionally built to be slightly loose.
Exactly.
Why on earth would you want a precision component to be loose?
Because of thermal expansion. If that bearing is destined for an industrial electric motor that runs incredibly hot, the heat from the rotor will transfer directly into the inner ring of the bearing. As metal heats up, it expands. That inner ring swells outward. The C3 clearance provides the empty space for that swelling metal to expand into.
And if a technician ignores the C3 code, grabs a standard bearing off the shelf that looks right, and hammers it onto the motor shaft.
The motor will run fine for about an hour.
An hour.
Maybe an hour. But as the rotor heats up, the inner ring expands. Because there is no extra clearance, the expanding ring violently pinches the steel balls against the outer race. The friction spikes, which generates even more heat, which causes even more expansion.
It just feeds on itself.
It is a rapid thermal runaway. The grease instantly cooks and turns to carbon. The steel balls suffer spalling, where chunks of metal actually flake off. The bearing seizes solid, and the motor burns out. All because someone ignored two letters on a part number.
This raises an important question regarding traceability and accountability. In consumer electronics, a part number is usually enough. But in the world of high-speed rotation, the sources emphasize the difference between model, part, serial, batch, and lot numbers.
Yes, the tracking is obsessive.
Why is this level of granular tracking necessary? Why does a manufacturer need to know exactly which batch of steel a specific turbine rotor was forged from 5 years ago?
Because of the high-stakes nature of failure and root cause analysis. If an aviation turbine rotor fails in flight, or a composite flywheel shatters in a data center, investigators reconstruct the failure. If metallurgical analysis reveals that the failure wasn't caused by misuse, but by a microscopic inclusion of slag left inside the steel during the original forging process,
You have a massive problem.
a huge problem.
Because if that batch of steel had a flaw, every other part made from that batch is a ticking time bomb.
Exactly. The manufacturer uses the lot number to instantly trace exactly which pouring of liquid steel that failed rotor came from. They cross-reference the lot number, trace the serial numbers of every other rotor forged from that exact same batch of metal, locate which machines around the world those specific serial numbers are installed in, and issue an emergency recall to ground them before they fail as well.
Wow.
At high RPMs, hidden metallurgical defects become lethal projectiles. Traceability is quite literally a matter of life and death.
But, entropy is a relentless force. Despite the perfect grain flow of forged steel, despite the thermal clearances, and despite the absolute precision of the manufacturing, these parts operate under relentless kinetic stress. Eventually, the metal wears, the grease dries out. Entropy always wins.
It always wins.
Which brings us to Section 5, the life cycle and maintenance of the core. How do we manage the inevitable degradation?
Well, rotating machinery rarely fails silently. It almost always tries to communicate its distress before a catastrophic event. You just have to know how to listen. The field of predictive maintenance is largely about translating the sensory output of a machine.
I found the section of the notes on the sounds of failure so visceral.
It's poetry in the Grum way.
Experienced technicians diagnose these machines using all of their senses. It's almost like acoustic,
medical diagnostics. You listen for the rumbling of a wheel hub, that low, rhythmic growl that changes pitch when you steer your car, indicating a pitted bearing race. You listen for the high-pitched squealing of a motor bearing that has run dry of lubrication, meaning metal is rubbing directly on metal. You use your eyes to look for the violent blue sparking of a failing armature commutator. And you use your nose, the unmistakable, acrid, burning smell of a fried stator, where the thermal limits of the copper insulation have been exceeded and the varnish is literally melting away.
It is sensory detective work, backed by rigorous maintenance rituals. And the first line of defense is always tribology.
Tribology, the science of friction and lubrication.
Yes. Lubrication is not just about making things slippery. In a high-speed roller bearing, a properly selected grease or oil creates an elastohydrodynamic film.
Elastohydrodynamic film, say that 3 times fast.
It's a mouthful, but what it means is under the immense pressure of the rolling elements, the oil momentarily turns into a nearly solid glass-like layer. It physically separates the microscopic peaks of the metal surfaces so they never actually touch.
Wait, they never touch?
If it's lubricated properly, no. If you lose that microscopic film, the metal micro-welds itself together and tears apart with every revolution.
And beyond lubrication, you have alignment and balancing. You can have a flawlessly manufactured electric motor bolted to a flawlessly manufactured industrial pump. But if the coupling joining their 2 shafts is misaligned by even the thickness of a piece of paper, every single revolution forces the shafts to bend.
It introduces a massive cyclical bending moment that will destroy the bearings in days.
So the technicians use precision laser alignment tools to bring the center lines of both shafts into perfect geometric harmony.
Right. And then there's dynamic balancing. If you have a massive industrial cooling fan, and over 6 months a layer of sticky industrial dust accumulates unevenly on one side of the fan blades, the center of mass shifts away from the physical center of the shaft.
Which means the heavy side pulls outward with more centrifugal force. It turns into an unbalanced washing machine on the spin cycle, violently shaking the concrete mounts until the structure cracks.
Exactly. You have to shut it down, map the vibration, and literally weld small counterweights to the light side of the fan to bring the mass back into equilibrium.
But all of these maintenance rituals rely on one fundamental assumption: that the machine is actually designed to be repaired.
Yes.
And this brings us to a major ethical tension in modern manufacturing: the ethics of repairability.
This is a hot topic.
Okay, let me push back on this organically, because I read the sources on the right to repair, and it frames OEMs locking down their parts as purely villainous. But look at it from an engineering perspective. Aren't sealed, non-repairable assemblies actually better for the consumer in many cases?
In what way?
If a wheel hub assembly or a washing machine motor is completely sealed from the factory, it keeps dirt out, it keeps moisture out, and it requires 0 maintenance from the user. You don't have to pack it with grease every 10,000 miles. The meantime between failures, the MTBF, is objectively longer for a sealed unit in a dirty environment, precisely because it removes the variable of user neglect.
From a pure reliability engineering standpoint, during the operational life of the product, you are absolutely correct. Sealing the system protects it from contamination and incompetent maintenance.
Right.
But the ethical tension does not arise while the machine is working. It arises at the end of that lifespan. A sealed bearing assembly might run flawlessly for 10 years, but when the grease inevitably degrades and the bearing finally fails, the design traps the consumer.
Because you can't just press out the $5 standard bearing.
Exactly. You are forced to throw away a massive, heavy, $300 cast iron hub assembly, or sometimes scrap an entire appliance, just to replace one degraded friction surface. The sources argue this crosses the line from engineering reliability into planned obsolescence.
And this tension has exploded into a massive legal battleground. The notes cite the Federal Trade Commission, the FTC's 2021 report called Nixing the Fix, which explicitly condemned how manufacturers use proprietary designs, software locks, and non-standard parts to restrict third-party repair.
And we are seeing severe legislative pushback now.
Yeah, like the sweeping right to repair legislation passed in Colorado in 2024. But the manufacturers aren't just giving up. They argue they are protecting intellectual property, and more importantly, they argue they're protecting safety.
And we have to acknowledge that the safety argument carries profound weight in specific, high-stakes contexts. We aren't just talking about fixing a toaster here.
Right.
If we're looking at a proprietary multi-axis CNC spindle rotating a heavy cutting tool at 30,000 RPM, or a complex medical centrifuge rotor handling hazardous biological samples, or the drive unit of an electric vehicle managing hundreds of amps of high voltage and massive torque vectoring at highway speeds. A poor repair is terrifying.
If someone rewinds an EV stator incorrectly, it could short out the battery pack or cause the wheel to lock up at 70 miles an hour.
Exactly. In those high-stress environments, a botched repair with inferior generic aftermarket parts isn't just a frustrating inconvenience, it is a lethal hazard. The manufacturer's argument is that locking down the repair process ensures that only certified technicians, using verified OEM components with the correct metallurgy and tolerances, touch the critical rotation paths.
But the pro-repair advocates counter that by saying safety is being used as a convenient smokescreen. Sure, lock down the high-voltage EV stator, but don't use that same logic to prevent a farmer from replacing a basic standard roller bearing on a combine harvester in the middle of a harvest.
Right.
Don't use software locks to prevent a consumer from swapping out a simple broken hub on a household fan.
It really is the struggle over ownership. When you buy a machine, do you own the physics of it, or are you just licensing the rotation from the manufacturer?
Which naturally forces us to pull back and look at the macro picture, the global footprint. Because the debate over throwing away a broken washing machine due to a sealed bearing inevitably leads to the environmental cost of manufacturing a replacement. Every time we throw away a massive chunk of metal because a tiny bearing failed, we have to make a new one.
And the environmental ledger for rotating components is staggeringly heavy. The vast majority of these components are forged from steel, cast from iron, or wound with copper. The extraction, the mining of iron ore and bauxite, and specifically the smelting and forging processes are massively energy intensive.
The IEA data from the sources is sobering. The steel industry alone accounts for roughly 8% of the total global energy system CO2 emissions. So when you look at massive industrial shafts, heavy stators, thick rotors, and dense flywheels, the embodied carbon in these machines is astronomical.
But the notes also provide the hopeful counter-narrative, the other side of the environmental coin. A brilliantly engineered, easily rebuildable steel shaft or a heavy-duty motor designed so that the stator can be easily rewound with new copper when the insulation fails is a masterclass in sustainability.
The text explicitly states, durability is sustainability.
I love that line.
If you build the center to last, if the Bannock of the machine holds the line, the rest of the complex machinery survives. You don't have to mine new iron ore, you just replace the wear surfaces.
Exactly. But maintaining that durable civilization requires a highly functioning, seamless global supply chain. And as the world pivots harder toward electrification and automation, that supply chain is becoming alarmingly vulnerable to specific choke points.
Like what?
The most critical bottleneck highlighted in the notes involves the rare earth elements we discussed earlier, specifically for the permanent magnets driving modern rotors.
Right. The neodymium and dysprosium required to make EV motors and wind turbines light and powerful enough to actually work.
The IEA issued a stark warning looking at 2024 data, noting that China exported a staggering 58,000 tons of rare earth magnets that year.
58,000 tons.
Yes. That level of geographic and industrial concentration means that the entire global production pipeline for electric vehicles, offshore wind turbines, advanced robotics, and sophisticated defense systems relies heavily on a single massive node.
It's a single point of failure for the global turning heart. A missing shipment of neodymium magnets can grind an EV production line to a halt. A missing proprietary CNC spindle can shut down an entire aerospace factory floor. The supply chain for rotation is incredibly tight. So what does this all mean? How do we navigate these supply chain choke points and the massive environmental footprint of the steel and copper?
Well, the sources point to some wild innovations on the horizon that might change the math entirely.
Tell me about them.
The most immediate transformative shift is the integration of AI into acoustic and vibration analysis. It's taking predictive maintenance to an entirely new level. Historically, you replaced a bearing on a rigid calendar schedule, regardless of whether it was actually worn or you waited until it catastrophically failed and destroyed the shaft.
Not ideal.
No. But today, we are blanketing rotating equipment with sensitive piezoelectric sensors.
They are essentially attaching stethoscopes to the machines and feeding the audio into neural networks.
Precisely. The AI algorithms listen to the acoustic signatures and the microscopic vibrational shifts of a spinning shaft in real time. Long before a human ear could hear the rumble of a failing bearing, the AI can detect the specific ultrasonic frequencies of a microscopic crack propagating in a bearing race.
It hears the crack growing.
Yes. And the system flags the operator and says, the inboard bearing on pump number 4 will fail in approximately 300 hours.
Which allows for a surgically precise, planned repair during a scheduled maintenance window, preventing a catastrophic failure that ruins the entire assembly.
And it saves millions of tons of steel from the scrapyard.
That's incredible.
And looking further ahead, we have the rise of digital twins. Before a massive turbine rotor is ever forged, engineers create a perfect digital simulation of it. They subject the digital model to simulated thermal expansion, torsional shear, and resonant frequencies to find the failure points in the math before they ever pour the physical steel.
In additive manufacturing, right, 3D printing metal. For decades, the shape of a rotor was limited by what a drill bit or a lathe could physically reach. With 3D metal printing, you can create a rotor with incredibly complex, fractal-like internal cooling channels that pull heat away from the core with unprecedented efficiency.
It opens up entirely new geometries.
And critically, on the supply chain front, the development of robust commercial-scale recycling methods to extract and re-refine neodymium from shredded end-of-life motors, breaking the reliance on raw mining.
All of these innovations point to a future where we respect the resources, the forces, and the physics of rotation much more deeply. We are moving from brute force engineering to hyper-optimized design. But, we pull the lens back even further, away from the AI algorithms and the geopolitical supply chains, we arrive at the grand arc of human history.
Yes, looking at the civilizational and philosophical impact, how has our mastery of this continuous rotation actually shaped who we are as a species?
Yep.
Because if you look at the brief history of rotation provided in the notes, it is a wild trajectory.
It spans thousands of years.
It starts around 3500 BCE in Mesopotamia. We have Sumerian sledges dragging heavy loads across the dirt, and then someone realizes that putting logs underneath, rolling friction instead of sliding friction, changes everything. The invention of the wheel, the axle, the potter's wheel, it was the dawn of mechanical leverage.
And from there, humanity spent millennia refining the concept. A massive leap forward occurred with the proliferation of medieval watermills. This was the moment we stopped relying purely on muscle power.
We harness nature.
We took the natural, kinetic, flowing energy of a river, captured it with a water wheel, and transferred that energy onto a massive wooden spinning shaft. That shaft carried the torque into a building to turn heavy millstones, grinding grain or powering trip hammers. It was the first true industrialization of rotation.
And then James Watt perfects the steam engine, figuring out how to take the erratic, expanding force of steam, pushing a piston, and use a heavy crankshaft and a massive flywheel to tame it into continuous, powerful rotation. That rotation drove the entire Industrial Revolution.
And it didn't stop there.
No. In 1822, Michael Faraday builds the first crude electric motor. He dips a wire in a bath of mercury next to a magnet, applies a current, and the wire begins to spin. He proves that the invisible, mysterious force of electromagnetism can be harnessed to produce physical, continuous rotation.
Right up to the hyper-precise, magnetically levitated cooling fans keeping global data centers from melting down today. The great shift, the defining characteristic of this historical arc, is that humanity successfully moved from hand repetition to machine repetition.
We outsource the work.
We took the grueling, repetitive labor of existence, grinding the grain, drawing the water, moving the heavy loads, and we outsourced it entirely to the rotating core. We built machines to do the repeating for us.
And this brings us full circle to the profound philosophical reflection in the sources, the metaphor of the inner flywheel. The notes remind us that engineering is not magic. We do not escape the brutal laws of physics. We merely negotiate with them.
We strike a bargain.
We ask nature for an axis, and we manage the friction as best we can. We use a heavy steel flywheel to store momentum and carry the system through the uneven, violent pulses of raw power. We balance the load.
And there is this incredible, almost tragic hidden labor to all of it. This returns us to the Bannock leadership metaphor we opened with. The nature of excellent infrastructure is that it disappears.
It becomes invisible.
Exactly. When a massive centrifugal pump works flawlessly, pushing millions of gallons of water through a city, we don't think about the torsional shear on the shaft, the thermal expansion of the bearings, or the specific carbon content of the seal. We just turn on the kitchen tap and call it water.
When the splined hub and the drive axle on a car operate perfectly, surviving millions of stress cycles without shattering, we don't think about the microscopic elastohydrodynamic film of oil keeping the metal alive. We just press the pedal and call it driving.
Right. We completely ignore the hidden spinning centers of our technology, and we ignore the thousands of hours of hidden human labor from the technicians, the engineers, and the maintenance crews, because their ultimate success looks exactly like nothing going wrong. They are invisible precisely because they are excellent.
It is the purest expression of the quiet compass. The rotor interacting with the magnetic field, the stator holding the boundaries, the shaft carrying the torque, the flywheel bearing the momentum, and the hub connecting it to the world. They are the quiet captains of our mechanical reality.
They don't demand the spotlight.
They do not demand the spotlight. They operate in the dark, bathed in oil, enduring unimaginable stress. They lead from the center, absorbing the shock, holding the precise alignment, and carrying the load, so that the rest of human civilization can keep moving forward uninterrupted.
We've spent all this time today exploring how physical machines use heavy flywheels and forged shafts to store momentum and transfer power smoothly through the rough, chaotic spots of nature. But look at your own life. When the external world pulses unevenly, when the stress spikes and the momentum drops, what is your personal inner flywheel? What are the quiet, unglamorous habits, the foundational routines, or the deep relationships that store your psychological momentum? What keeps you spinning smoothly, holding your center when the energy drops and the world around you gets chaotic? Keep looking closely at the hidden rotation, both in the machines around you and within yourself. Thanks for joining us on this deep dive.